All right, so welcome back to another video where I prepare for my new job 525 by learning, by mastering network automation. I already have a lot of experience with it, but I just want to make sure because I think that's the topic that I'm studying for my JNCIE SP as well, but I don't know how advanced esoteric knowledge about BGP is going to help me from day one. I think I'll be if I review, brush up, master some network automation concepts, I think I'll be much more widely effective on day one. So I'm going to continue to study for my IESP because, of course, that's going to help me overall in my career opportunities and stuff long term. But short term for this job on the 25th, I really think brushing up on network automation is going to give me the most bang for my time that I have before I start. Okay, so here's the book. We'd already gone over with it. So here's how this is going to work. I'm still working at my other job. My new job doesn't start until the 25th. So I'm going to keep this video private. When I upload it, it's going to be scheduled to go live on the 25th. So until then, this is a private video. Let's see here. So I bookmarked where we left off last time. I think we still are going to do a lot of reading. Unfortunately, it is, that's to toggle the bookmark. This is a see my bookmark. So yeah, we're going to jump. So let's go over, in the last video, I highlighted something that I thought was very important to keep in mind. So this is the where to start on the job, which I'm going to be doing on the 25th. You want to focus on read-only things and focus on using automation to troubleshoot and gather information. You can then use automation to flow the information that is gathered into ticketing systems or chat applications. And soon you have started to build a workflow. This safe start read-only evolution helps teams build confidence with automation and familiarity with the tools. So this is what I'm planning to do on day one. Anything where we're checking any ticketing system, I'm planning to kind of get in there and see if I can automate that sort of thing. I want to use the ticketing systems to my advantage for kind of representing what automation can do. All right, so, but let's jump over to the location where I left off last time. All right, and let's just get started. I will toggle the bookmark and begin to read. Review of TCP/IP protocol suite and Python. Welcome to the new exciting age of network engineering. When I started working as a network engineer at the turn of the millennium, the role was distinctly different than the network engineering role of today. At the time, network engineers mainly processed domain-specific knowledge to manage and operate local and wide area networks using the command line interface. While they might occasionally cross over the discipline wall to handle tasks normally associated with systems, administration, and developers, there was no explicit expectation for a network engineer to write code or understand programming concepts. That is no longer the case today. Over the years, the DevOps and software-defined networking, SDN movement, among other factors, have significantly blurred the lines between network engineers, systems engineers, and developers. The fact that you have picked up this book suggests that you might already be an adopter of network DevOps, or maybe you are considering going down that path of checking out network programmability. So myself, I am already an adopter of network DevOps. Maybe you have been working as a network engineer for many years. Drink to that. Just drinking water. Just as I had, and wanted to know what the buzz around the Python programming language is all about. You might even have been fluent in the Python programming language, but wonder what its applications are in the network engineering field. If you fall into any of these camps or are simply just curious about Python in the network engineering field, I believe this book is for you. So yep, I fall into the camp of an adopter of network DevOps, and I fall into the camp of the camp of wondering what its applications are in the network engineering field. I mean, I already know to a large extent, but I have more to wonder about that I'm hoping this book will show me the whole wide world and not just what I already know. So I definitely fall into that camp. If you fall into any of these camps or are simply curious about Python in the network engineering field, which of course I am, I believe this book is for you. Okay, so this book's definitely for me. So Python network engineering, this book, it blends the two of them. There are many books that have already been written that dive into the topics of network engineering and Python separately. I do not intend to repeat their efforts with this book. Instead, this book assumes that you have some hands-on experience of managing networks, as well as a basic understanding of network protocols. It's helpful if you're already familiar with Python as a language, but we will cover some basics later in the chapter. You do not need to be an expert in Python or network engineering to get the most out of this book. This book intends to build on the basic foundations of network engineering and Python to help readers to learn and practice various applications that can make their lives easier. In this chapter, we will do a general review, In this chapter, we will do a general review, some of the networking and Python concepts. So kind of a bad mark for this book already. It looks like there's a grammar error. We will do a general review. Oh, no. I just didn't see the word of. Sometimes I don't see small words like that. In this chapter, we will do a general no. They flipped the words is what happened. In this chapter, we will do a general review, so they meant to say of some of the networking and Python concepts. I mean, you can see how much little typos like that kind of throw me for a loop. So I tend to prefer books that really don't have very many of those. I'm kind of upset that this book has one on page like 2. I do have another book that might be more exciting, and kind of just skimming through it. There's a lot of concepts in that book that like, for example, I was talking about the unicorn environments that this book seems to be hoping you're going to be working in. The other book had a whole section about not what that unicorn environment looks like, but how you can tell if you're not a part of that unicorn environment. And it actually exposed me to a really important concept called closure that I had worked with and seen every day, but I didn't really know what to call it or what it was. And closure is the idea of people being awarded access, people being awarded opportunities, awarded information. So if you have a system that the whole floor is not allowed to access, and somebody has gained access, and now using that access, they get a special advantage and they get promoted. That person has closure. They have access to things that are closed off to other people, and they have an unfair advantage. And not only that, they get to make all the decisions. They get to, because they're the only one with the access to the information. So a more ideal environment, where everyone has joint responsibility and can work together and share information. And you get a more variety of opinions, and you get to have things happen more concurrently and not just wait on the one person who has somehow gotten that special access, special permission. And it's more of I think, a fun environment to work into, one where there's more joint responsibility, because you're not going to constantly be hit by roadblocks. It's more about solving the issue. It's not about solving the issue of not having the tools you need to solve the issue. Kind of that analogy I made with a ditch digging company not allowing shovels, not to mention backhoes or even more modern tools than that. All right, so yeah. The rest of the chapter should set the level of expectation of the prior knowledge required to get the most out of this book. If you want to brush up on the contents of this chapter, there are lots of free or low-cost opportunities to bring you up to speed, which I love. I'm a big fan of if you don't have to spend extra for it, don't spend extra for it. Do it for free. You can't buy education. Education is something you do. It's not something you buy. So the time you spend even going and shopping for an education is time you could have spent actually looking at the materials that are available for free. I would recommend the free Khan Academy and the Python tutorials. And big props to this book too for recommending Khan Academy. I am a huge supporter of Khan Academy. Unfortunately, not donation-wise yet, but as I get older and hopefully more successful, that actually might be something I would consider doing. This chapter will pay a very quick visit to the relevant networking topics at a high level without going too much into the details. Judging from my experience of working in the field, a typical network engineer or developer might not remember the exact transmission control protocol, TCP, state machine to accomplish their daily tasks. I know I don't, and I'll admit I've never heard of it being recalled as a state machine. Are they talking about? But yeah, I don't know what they mean. But they would be familiar with the basics of the open systems interconnection OSI model, which is please do not throw sausage pizza away, physical, data link, network layer, transport layer, session, presentation, application. So it's 7-layer OSI model. The TCP and datagram protocol operations. So TCP is a persistent connection and it has a 3-way handshake. And then if anything is lost, it's got sequence numbers. So it'll be able to tell, oh, IP received one packet. I received packet 1, 2, 3, but then I received packets 5, 6, and 7. So you got to resend me packet 4 and 5. UDP, nothing like that. If I don't get it, I don't get it. And if you send it, you're not going to know whether or not I received it. It's connectionless. Different IP header fields and other fundamental concepts. I guess I'm not sure what they mean by different IP header fields. Maybe they're talking about the ports, like you would form a SSH connection on port 22. They might be talking about QoS stuff, bit markings, IP precedence values, or just stuff that they might be talking about ACLs as well, stuff that you would use to match traffic and make decisions based on your matches. We will also look at a high-level review of the Python language, just enough for those readers who do not code in Python on a daily basis to have ground to walk on for the rest of the book. Specifically, we will cover the following topics: an overview of the internet, the OSI and client-server model, TCP, UDP, and IP protocol suites, Python syntax, types, operators, and loops, extending Python with functions, classes, and packages. Of course, the information presented in this chapter is not exhaustive. Please do check out other references for further information if required. As network engineers, we are typically challenged by the scale and complexity of the network we need to manage. They range from small home-based networks, medium-sized networks that make a small business go, to large multinational enterprise networks that span the globe. The biggest network of them all, of course, is the internet. Without the internet, there would be no mail, websites, API, streaming media, or cloud computing as we know it. Therefore, before we dive deeper into the specifics of protocols and Python, let us begin with an overview of the internet. So an overview of the internet. What is the internet? This seemingly simple question might receive different answers depending on your background. The internet means different things to different people. The young, the old, students, teachers, business people, poets could all give different answers to the same question. So I'm not quite sure where they're going with this, because I'm not sure how this is going to help a experienced network engineer master Python networking, but I'll keep reading. At this point, I'm kind of tempted to switch away from this book because I really got a limited amount of time. And the other thing I have that will be really valuable is there's a really great GNS course on network automation that I could go back over. And then I do have another book that, as I mentioned before, I really liked. But I was hoping to get through more than one resource. So let's just keep going on this book. To a network engineer, the internet is a global computer network consisting of a web of internetworks connecting large and small networks together. In other words, it is a network of networks without a centralized owner. Take your home network as an example. It might consist of a device that integrates the functions of routing, Ethernet switching, and wireless access points connecting your smartphones, tablets, computers, and internet-enabled TVs together for the devices to communicate with each other. This is your local area network, LAN, which it's kind of not, it is your WAN, but depending on your home network, you could have some VLAN set up on it. So, but yeah, I don't disagree. When your home network needs to communicate with the outside world, it passes information from your LAN to a larger network. It's often appropriately named the Internet Service Provider, ISP. The ISP is typically thought of as a business that you pay to get online. They are able to do this by aggregating small networks into bigger networks that they maintain. Your ISP network often consists of edge nodes that aggregate the traffic to their core network. The core network's function is to interconnect these edge networks at a higher speed via a higher speed network. At special edge nodes, your ISP is connected to other ISPs to pass your traffic appropriately to your destination. The return path from your destination to your home computer, tablet, or smartphone may or may not allow the same path through, or not follow the same path through all of these networks back to your device, while the source and destination remain the same. That I'm really glad they pick up on, because that's something that really only a network engineer has a good understanding of. The layperson really doesn't think into it in that depth. But yeah, that's 100% right. Just because you have a letter you're sending to your friend in Los Angeles doesn't mean that it's going to travel from your apartment in New York to their apartment in Los Angeles using the same route as it will when they reply, and it's traveling from their apartment in Los Angeles to your apartment in New York. The same thing applies to computer networking, and choosing the path that it travels in is pretty much one of the fundamental things you do as a network engineer. Make sure those paths make sense. They are capable. It could be going through a path that, why does the mailman have to walk through a bog with alligators, and then when it can just drive across the bridge, So those are kind of, I think that's a good explanation of network engineering. Let's take a look at the components making up this web of networks. Servers, hosts, and network components. Hosts are end nodes on the network that communicate to other nodes. In today's world, a host can be a traditional computer, or it can be a smartphone, tablet, or TV. With the rise of Internet of Things, IoT, the broad definition of a host can be expanded to include an Internet Protocol IP camera, TV set-top boxes, and the ever-increasing types of sensors that we use in agriculture, farming, automobiles, and more. With the explosion of the number of hosts connected to the internet. All of them need to be addressed, routed, and managed. The demand for proper networking has never been greater. Most of the time when we are on the internet, we make requests for services. This could be viewing a web page, sending or receiving emails, transferring files, and so on. These services are provided by servers. As the name implies, servers provide devices to multiple nodes and typically have higher levels of hardware specification. In a way, servers are special supernodes on the network that provide additional capabilities to their peers. We will look at servers later in the client-server model section. If you think of servers and hosts as cities and towns, the network components are the roads and highways that connect them together. In fact, the term information superhighway comes to mind when describing the network components that transmit the ever-increasing bits and bytes across the globe. In the OSI model that we will look at in a bit, these network components are layer 1 to 3 devices that sometimes venture into layer 4 as well. They are layer 2 and 3 routers and switches. That's kind of, I don't like that sentence because it should be, they are either layer 3 and layer 2 routers and switches, or they are layer 2 and layer 3 switches and routers. Of course, you can have a multi-layer switch, and then on routers, you can have a layer 2 VPN, you can have bridging, you can have layer 2 on routers, but the general term for router and switch does imply what layer they are on, switches being on layer 2, routers being on layer 3. As well as layer 1 transports such as fiber optic cables, coaxial cables, twisted copper pairs, and some dense wavelength division multiplexing, DWDM equipment, to name a few. Collectively, hosts, servers, storage, and network components make up the internet as we know it today. The rise of data centers. In the last section, we looked at different roles that servers, hosts, and network components play in the internetwork. Because of the higher hardware capacity that servers demand, they are often put together in a central location to be managed more effectively. We often refer to these locations as data centers. Enterprise data centers. In a typical enterprise, the company generally has the business needs for internal tools such as emailing, document storage, sales tracking, ordering, HR tools, and a knowledge sharing intranet. These services translate into file and mail servers, database servers, and web servers. Unlike user computers, these are generally high-end computers that require a lot of power, cooling, and network connections. A byproduct of the hardware is also the amount of noise they make, which is not suitable for a normal workspace. The servers are generally placed in a central location called the main distribution frame, MDF. In the enterprise building, they provide the necessary, in the enterprise building to provide the necessary power feed, power redundancy, cooling, and network connectivity. To connect to the MDF, which I think it stands for mainframe distribution frame. No, main distribution frame. The user's traffic is generally aggregated at a location closer to the user, which is sometimes called the intermediate distribution frame, IDF, before they are bundled up and connected to the MDF, main distribution frame. It is not unusual for the IDF, intermediate distribution frame, -MDF, main distribution frame spread to follow the physical layout of the enterprise building or campus. For example, each building floor can consist of an IDF that aggregates to the centralized MDF on another floor in the same building. If the enterprise consists of several buildings, further aggregation can be done by combining the building's traffic before connecting them to the enterprise data center. Enterprise data centers generally follow the network design of 3 layers. Okay, so this I know about from networking school. The other, I've never heard the terms IDF and MDF, intermediate distribution layer and main distribution, frame and main distribution frame. So I'm really glad to have a exposure to that. These layers are access layers, distribution layers, and a core layer. So that I know all about through networking school, and you can get Cisco design guides that explain that. And it's I think it was part of the, it's part of the CCNP curriculum. Of course, as with any design, there are no hard rules or one-size-fits-all model. The 3-layer designs are just a general guide. As an example, to overlay the 3-layer design on our user intermediate data frame, intermediate distribution frame dash main distribution frame example earlier, the access layer is analogous to the ports each user connects to. The IDF can be thought of as the distribution layer, while the core layer consists of the connection to the MDF, main data or main distribution frame, and the enterprise data centers. This is, of course, a generalization of enterprise networks, as some will not follow the same model. Cloud data centers. With the rise of cloud computing and software, or infrastructure as a service, IaaS, the data centers the cloud providers have built are really big in scale, sometimes referred to as hyperscale data centers. What we refer to as cloud computing is the on-demand availability of computing resources offered by the likes of Amazon, Microsoft, and Google without the user having to directly manage the resources. Because of the number of servers they need to house, the cloud data centers generally demand a much, much higher capacity of power, cooling, and network capacity than any enterprise data center. Even after working on cloud provider data centers for many years, every time I visit a cloud provider data center, I am still amazed at the scale of it. Just to give examples of the sheer scale of them, cloud data centers are so big and power hungry that they are typically built close to power plants where they can get the cheapest power rate without losing too much efficiency during the transportation of the power. Their cooling needs are so high that some are forced to be creative about where their data center is built. Facebook, for example, have built their Luella data center in northern Sweden, just 70 miles south of the Arctic Circle, in part to leverage the cold temperature for cooling. Any search engine can give you, some of the astounding numbers when it comes to the science of building and maintaining cloud data centers for the likes of Amazon, Microsoft, Google, and Facebook. The Microsoft data center in West Des Moines, Iowa, for example, consists of 1.2 million square feet of facility on 200 acres of land and required the city to spend an estimated $65 million in public infrastructure upgrades. At the cloud provider's scale, the services that they need to provide are generally not cost-effective or feasible to be housed in a single server. The services are spread between a fleet of servers, sometimes across many different racks, provide redundancy and flexibility for service owners. The latency and redundancy requirements, as well as the physical spread out of servers, put a tremendous amount of pressure on the network. The number of interconnections required to connect these server fleets equates to an explosive growth of network equipment such as cables, switches, and routers. These requirements translate into the number of times these network equipments needs to be racked, provisioned, and managed. A typical network design would be a multi-staged CLOS, close network. In a way, cloud data centers are where network automation becomes a necessity for speed, flexibility, and reliability. If we follow the traditional way of managing network devices via a terminal and command line interface, the number of engineering hours required would not allow the service to be available in a reasonable amount of time. This is not to mention that human repetition is error-prone, inefficient, and a terrible waste of engineering talent. To add further complexity, there is often the need to quickly change some of the network configuration to accommodate rapidly changing business needs. Personally, cloud data centers are where I started my path of network automation with Python a number of years ago, and I've never looked back since. For me, it's different. I started in ISP, and it's going to be quite a bit different. It's not a bunch of devices all in one square footage. It's just a bunch of different kinds of devices spread out all over the United States. Lots of different kinds of devices too. So I kind of had a different experience than this author. So that's a good thing, because now I can get a wider breadth of perspective. Edge data centers. If we have sufficient computing power at the data center level, why keep anything anywhere else but at these data centers? All the connections from clients around the world can be routed back to the data center servers providing the service, and we can call it a day, right? The answer is, of course, it depends on use cases. The biggest limitation in routing the request and session all the way back from the client to a large data center is the latency introduced in the transport. In other words, large latency is where the network becomes a bottleneck. Of course, any elementary physics textbook can tell you that the network latency number would never be zero. Even as fast as light can travel in a vacuum, it still takes time for physical transportation. In the real world, latency would be much higher than light in a vacuum. Why? Because the network packet has to traverse through multiple networks, sometimes through undersea cable, slow satellite links, 3G or 4G cellular links, or Wi-Fi connections. Kind of a funny story. One of the things I needed to do, like in my first year after networking school, was provide latency test results. I forget what it was, like RFC 2544, something like that, test results. And you get latency, jitter, and packet loss. Well, oh no, you get latency, frame loss, and I don't think you would get jitter for that one. I think you would, but anyways, I don't remember. That was a while ago. I'm into DevOps now, and I'm moving into a senior network engineer position shortly. But kind of a funny story is the results I was getting was like 80 milliseconds of latency, which seems like a lot, but this was a circuit from like New York to LA. And the customer was not happy with these circuits. They wanted them to be under 20 seconds of milliseconds. So a guy I was working with was like, wait a minute, they want under 20 seconds of latency for a circuit from New York to LA. Okay, well, let's look up the speed of light. Let's look up the geographical distance between those two cities, and let's see, how reasonable this expectation is. So the speed of light is going to be meters per second. So how many meters between New York and LA? So it's going to be 3944 kilometers. So that's going to be that times 1,000 meters. So let's set up in Notepad the math here. So it's going to be able to travel, and we're providing them like a fiber connection. So fiber connect, and yeah, as this book said, you actually can't provide a fiber connection completely end to end. It's going to travel through whatever travels through. I think in our case it was going to be fiber end to end. I'm not sure the specifics, and even if I were, I wouldn't want to share them as part of confidentiality. But definitely I can say that this customer was wanting a large, a long geographical connection. And I'll show you why they're being unhappy with a result like 80 milliseconds is quite unreasonable. And again, I don't know if that was, I don't even remember the exact details. And even if I did, I could not share them to confidentiality. But this is per 1 second. So the ratio of that number to 1, we're going to equal the same ratio of the number of meters to, so yeah, let's flip this ratio so that it's easier to work with. Okay, so now we're going to see, so we want the number of seconds. So the number of meters are going to be 3944 times 1,000. So 39, I think it was, yeah, 3944 times 1,000. Copy that. Okay, so now to get the number of seconds that are the lowest amount of seconds possible for a circuit like this, we're going to, of course, multiply this value by 1 divided by that value. Then the meters, yeah, the meters will cancel out, and we'll just have the number of seconds that it will take. So we got to multiply this number. Oops. Okay, so that's going to be times, now we need some parentheses, 1 divided by 299,792,458 equals, so it's going to take 0.0131557 seconds minimum. So let's convert that to milliseconds. So I believe the way you do that is so I think it's going to be like 13. So I'll just convert that using a calculator. Yeah, because microseconds is going to be, yeah, so let's see how many. Oh, right. It's going to be, okay. That's the wrong number I pasted in there. I was about to say that doesn't seem right. Yeah, I was right. So this is the absolute fastest you can do if you were shooting a beam of light through a vacuum from New York to LA. it would still take you more than 13 milliseconds. So you tell me if 20 milliseconds is something we can aim for and deliver. I mean, I think 80 is probably, when we say it's the best we can do, it's probably the best we could have done. It's just a long distance. Like even the speed of light, something we think of as is this really like impossibly fast speed. New York to LA, speed of light, 13 milliseconds, and that's when you're talking about as instant as possible communications. That can be pretty slow. It can be hard to have a conversation with somebody when you've got to wait. You can't respond to them in real time. The human mind really needs that instant recognition in order to have a conversation, because otherwise you just can't tell when you need to talk, and they'll constantly be talking over each other. All right, so let's continue the reading. Yeah, it's kind of a funny aside. But yeah, let's continue the reading. So yeah, what if we need to reduce the network latency? One solution would be to reduce the number of networks the end user requests traverse through. Be as closely connected to the other end as possible at the edge where the user enters your network, and place enough resources at the edge location to serve your request. This is especially common for servicing media content such as music and videos. So yep, in our example where it takes more than 13 milliseconds just to shine a light through a vacuum from New York to LA, yeah, of course, if we do it from the Midwest to LA, it will take less time to do that. So yeah, placing things closer is a surefire way you can reduce latency. Let's take a minute and imagine that you are building the next generation of video streaming service. In order to increase customer satisfaction with smooth streaming, you would want to place the video server as close to the customer as possible, either inside or very near to the customer's ISP. Also, for redundancy and connection speed, the upstreaming of the video server farm would not just be connected to one or two ISPs, but all the ISPs that I can connect to reduce the hop count. All the connections would be with as much bandwidth as needed to decrease latency during peak hours. This need gave rise to the peering exchanges, edge data centers of big ISP and content providers. Even when the number of network devices is not as high as cloud data centers, they too can benefit from network automation in terms of increased reliability, flexibility, security, and visibility network automation brings. We will cover security, Chapter 6, network security with Python, and visibility, Chapter 7, network monitoring with Python, Part 1, and Chapter 2, network monitoring with Python, Part 2. In later chapters of this book, as with many complex subjects that break the complexity by dividing the subject into smaller digestive pieces, networking is based on the concept of layers. Over the years, there are different networking models that have been developed. We will take a look at two of the most important models in this book, starting with the OSI model. The OSI model, no network book is complete without first going over the OSI model. The model is a conceptual model that componentizes the telecommunication functions into different layers. The model defines 7 layers and each layer sits independently on top of another one with defined structures and characteristics. For example, in the network layer, which is going to be layer 3, IP is located on top of the different types of data link layers, such as Ethernet or frame relay. The OSI reference model is a good way to normalize different and diverse technologies into a set of common languages that people can agree on. This greatly reduces the scope for parties working on individual layers and allows them to look at specific tasks in depth without worrying too much about compatibility. So this is a really good concept. One thing I would say is, yeah, if you're gonna, yeah, just removing the complexity, talking about what you're talking about, that's really important, and that's what the OSI model is meant to do. If you're talking about the media layers, there's really no need to mention the host layers, and the people behind the OSI model took it upon themselves to organize everything so that that is true. The OSI model was initially worked on in the late 1970s and was later published jointly by the International Organization for Standardization, ISO, which is now known as the Telecommunication Standardization Sector of the International Telecommunication Union, ITU-T. It is widely accepted and commonly referred to when introducing a new topic in telecommunications. So let's read this graphic. Can I make it bigger? I cannot. Okay. So we know that it's, please do not throw sausage pizza away. But let's read so that's the layer. And now we've got media layers and we've got host layers. So layer 1, physical, the protocol data unit, so the thing that actually is exchanged, those are referred to as bits at layer 1. And the function is transmission and reception of raw bit streams over a physical medium. So things that would be on layer 1 are the wires themselves. Those are for transmission and reception of raw bit streams over a physical medium. The form factors of the ports, that's all layer 1, the physical layer. Yeah, I mean, those are the main ones. I'm sure there's more. Let's move up to layer 2 though. Layer 2 is the data link, and so you have heard me in previous videos talk about frame packet segments. So when I say frame, I'm talking about the data link layer, layer 2. That's the protocol data units that is exchanged. It's a frame. The function is reliable transmission of data frames between 2 nodes connected by a physical layer. Layer 3, the protocol data unit, PDU, is referred to as a packet. Layer 3 is the network layer. It's the last of the media layers. The function is structuring and managing a multi-node network, including addressing, routing, and traffic control. Into the host layers, the transport layer, layer 4, and for some reason that's in a different shade. It's in a different shade of green because the protocol data unit is going to be separate from the other 4 layers in the host layers, and it is referred to as a segment when it's TCP, but if it's UDP, it's actually going to be referred to as a datagram. So that's something I actually didn't know. I was just referring to everything as segments. So thank you to the authors of this book for having that be really clear to me, because yeah, that like using Wireshark and using stuff, yeah, if I see a datagram, I know it's a UDP. If I see a segment, I know it's TCP. So really good to know. Reliable transmission of data segments between points on a network, including segmentation, acknowledgement, and multiplexing. That's the transport layer. Moving up on the host layers, we've got the session layer, and this is just referred to as data. This is just data exchanging. Protocol data unit is data, and the function is managing communication sessions, i.e. continuous exchange of information in the form of multiple back and forth transmissions between two nodes. Presentation layer, also data, but the function is translation of data between a networking service and an application, including character encoding, data compression, and encryption/decryption. Layer 7, application layer, also data, function, high-level APIs, including resource sharing, remote file access. So yeah, all important stuff. You're going to see FTP on layer 7, all these Flask exercises where we set up an API. We're doing stuff, we're getting experience on layer 7. When you do an upgrade on a device, you're getting experience at layer 7 because you're sharing those resources. You're pulling from an FTP server. Layer 6, when you're setting up your SSH keys, you're doing stuff on layer 6. That's encryption, decryption, that sort of stuff. SSH versus Telnet, the fact that it's encrypted in SSH and not in Telnet, that's a concept that happens on layer 6. SSL encryption and stuff, that's a layer 6 concept. Layer 5, managing communication sessions, continuous exchange of information in the form of multiple back and forth transmissions between two nodes. So that is a bit more unclear to me. I would think that the BGP keep alives, any keep alive messages, that would kind of fall under layer 5. Those BGP neighborships are likely happening on layer 5. Layer 4, yep, so now you've got your sockets, which is an IP address, colon, a port. That's a layer 4 concept. And of course, all your TCP, UDP stuff, it's all spelled out there, right there for you on layer 4, what layer 4 is. Layer 3, here you got your IP addresses, you got your routing tables, you've got any sort of multi-node networking is on layer 3. Layer 2, this is just between two nodes, so we're not talking about routers anymore. We're talking about one single broadcast domain. And then layer 1, you've got your wires, you've got the things you can touch, those are all physical. Around the same time period as OSI model development, the internet was taking shape. The reference model the original designer used is often referred to as the TCP/IP model. The TCP and the IP were the original protocol suites contained in the design. This is somewhat similar to the OSI model in the sense that they divide end-to-end data communication into abstraction layers. What is different is the model combines layers 5 to 7 in the OSI model in the application layer, while the physical and data link layers are combined in the link layer. Both OSI and TCP/IP models are useful for providing standards for end-to-end data communication. However, for the most part, we will refer to the TCP/IP model more in this book, since that is what the internet was originally built on. We will refer to the OSI model when needed, such as when we are discussing the web framework in the upcoming chapters. Just like models at the transport layer, there are also reference models that govern communication at the application level. In the modern network, the client-server model is what most applications are based on. We will take a look at the client-server model in the next section. So one thing that's important to know, and I won't read out that graphic, is that often you will hear in networking, and this was a big point of confusion for me in networking school. People throw out layer 2, layer 3, and you won't know what model they're talking about because there are layers on the TCP/IP model. like we're combining layers 5 and 7 in the OSI model in the application layer. Well, and then we also have a link layer. So we've got layers in IP in the TCP/IP model. So when you tell me layer 2, and you don't tell me whether you're talking about the OSI model or the TCP/IP model, in networking school, before I realized that kind of the standard of what people talk about is the OSI model, I didn't know what you're saying to me because you're basically saying layer 2, but you're assuming I know which model you're talking about. We've got 2 different models with layers. So that's something that was actually never quite cleared up for me, but as I kind of got more experience, I kind of realized that one, a lot of network engineers don't really talk about this sort of thing very often. And 2, it's assumed that it's the OSI model typically. All right, client server model. The client server, we will refer to the OSI model when needed, such as when discussing the web framework and the upcoming channels. Just like models at the transport layer, there are also reference models that govern communication at the application level. In the modern network, the client server model is what most applications are built on. We will take a look at the client server model in the next section. Client server model. The client server reference models are demonstrated a standard way for data communication between 2 nodes. Of course, by now, we all know that not all nodes are created equal. Even in the earliest advanced research projects, adjacency network, ARPANET days, there were workstation nodes and there were server nodes with the purpose of providing content to other nodes. These server nodes typically have higher hardware specifications and are managed more closely by engineers. Since these nodes provide resources and services to others, they are appropriately referred to as servers. Servers typically sit idle waiting for clients to initiate requests for their services. This model of distributed resources that are requested by the client request is referred to as the client server model. Why is this important? If you think about it for a minute, the importance of networking is greatly highlighted by this client server model. Without the need to transfer services between clients and servers, there is really not a lot of need for network interconnections. It is the need to transfer bits and bytes from the client to the server that shines a light on the importance of network engineering. Of course, we are all aware of how the biggest networks of them all, the internet, has been transforming the lives of all of us and is continuing to do so. You might be asking, how can each node determine the time, speed, source, and destination every time they need to talk to each other? This brings us to network protocols. Network protocol suites. In the early days of computer networking, protocols were proprietary and closely controlled by the company who designed the connection method. And as I mentioned in a tangent earlier, we might be going back to those days because SpaceX, at least when I checked, probably more than 3 years ago, is hiring specifically a wireless network architect to design custom routing protocols for their satellite constellation network. So we might be going back to those old days. If you were using Novell's IPX/SPX protocol in your hosts, these same hosts would not be able to communicate with Apple's AppleTalk hosts and vice versa. These proprietary protocol suites generally have analogous layers to the OSI reference model and follow the client-server communication method, but are not compatible with each other. The proprietary protocols generally only work in LANs that are closed without the need to communicate with the outside world. When traffic does need to move beyond the local LAN, typically an internet translation device such as a router is used to translate from one protocol to another. For example, in order to connect an AppleTalk-based network to the internet, a router would be used to connect and translate the AppleTalk protocol to an IP-based network. The additional translation is usually not perfect, but since most of the communication happened within the LAN in the early days, it was accepted by the network administrators. However, as the need for inter-network communication rises beyond the LAN, the need for standardizing the network protocol suites becomes greater. The proprietary protocols eventually gave way to the standardized protocol suites of TCP, UDP, and IP, which greatly enhanced the ability of one network to talk to another. The internet, the greatest network of them all, relies on these protocols to function properly. In the next few sections, we will take a look at each of the protocol suites. Transmission Control Protocol. The TCP, Transmission Control Protocol, is one of the main protocols used in the internet today. If you have opened a web page or have sent an email, you have come across the TCP protocol. The protocol sits at layer 4 of the Osi model, and it is responsible for delivering the data segments between two nodes in a reliable and error-checked manner. The TCP, Transmission Control Protocol, consists of a 160-bit header that contains, among others, source and destination ports, a sequence number, an acknowledgement number, control flags, and a checksum. And some of these flags are going to be SYN, SYNAC, ACK, FIN, push is going to be one. ECN, echo is going to be one. Congestion, window. Yeah. So, yeah, let's just keep reading. Functions and characteristics of TCP. Actually, it might show me here what, So yeah, CWR, that's what I was thinking. So yeah, so there's the flags right there. NS, CWR, ECE, URG, ACK, ACK, PSH, push, RST, reset, CYN, SYN, FIN, FIN. So FIN, SYN, reset, push, acknowledge, urgent, ECN echo or EC echo, CWR, which is congestion window reset, and NS, which I'm not sure what that is. Yep, and then you can see we've got the source port, the destination port, the sequence number, the acknowledgement number if ACK is set, data offset, reserve field or flags, window size, checksum, urgent port pointer if we've got urgents set, and then we've got options. Functions and characteristics of TCP, Transmission Control Protocol. TCP uses datagram sockets. That's interesting because we saw in the previous page that UDP was referred to as a datagram. And TCP was referred to as a, not a socket, but a, because you've got bits, you've got frames, it's referred to as a segment. So I'm surprised to see the word datagram and TCP together. I would think that would be, right here, datagram, UDP, segment, TCP, I would think they would use the term segment. So I'm not sure what's going on there. Or ports to establish a host-to-host communication. The standard body called Internet Assigned Numbers Authority, IANA, designs well-known ports to include certain services, such as port 80 for HTTP or web, and port 25 for SMTP, mail. The server in the client-server model typically listens to one of these well-known ports in order to receive communication requests from the client. The TCP connection is managed by the operating system by the socket that represents the local endpoint for connection. The protocol operation consists of a state machine where the machine needs to keep track of when it is listening for an incoming connection during the communication session, as well as releasing resources once the connection is closed. Each TCP connection goes through a series of states such as listen, SYN sent, SYN received, established, FIN wait, close wait. So close wait is, close wait, closing, last ACK, time wait, and close. So time wait's kind of an interesting one to know about because time wait depends on the order in which the TCP connection was closed. So if I close it, I'm going to go into a time wait because I'm going to say, we're done talking. Oh, but by the way, let me listen to what you have to say. If you were in the middle of saying something, but I just hadn't heard it yet, I'll give you the chance. Oh, okay, I heard it. Thank you. Now we're closing. So it does that with a full minute by default, which can be a lot. So that's a really important one to know if you're doing network automation. I guarantee you they won't bring it up in this book. They might. But if they do, huge props to this book. I will be really impressed because this is something I learned through hard-earned experience, that if you're on one server and you're connecting to 10,000 devices, you want to make sure to close your connections on each of those 10,000 devices so that each one of those single devices goes into that time wait, and your ports, TCP ports, close instantly. If you keep forming new connections, you don't have the possibility for port exhaustion quite as easy as you would, because depending on how many devices you're trying to connect to, you can run out of ephemeral ports to make those connections from. All right, TCP messages and data transfer. The biggest difference between TCP and UDP, which is its close cousin on the same layer, is that it transmits data in an ordered and reliable fashion. The fact that the TCP operation guarantees delivery is often referred to TCP as a connection-oriented protocol. It does this by first establishing a three-way handshake to synchronize the sequence number between the transmitter and the receiver, SYN, SYNAC, ACK. The acknowledgement is used to keep track of subsequent segments in the conversation. Finally, at the end of the conversation, one side will send a FIN message, the other side will ACK the FIN message, as well as sending a FIN message of its own. So it goes FIN, FIN, ACK, FIN. It's not a back and forth. The FIN initiator will then ACK the FIN message that it is received. So it's a FIN ACK, FIN ACK, but it's a FIN ACK, FIN ACK. Many of us who have troubleshot a TCP connection can tell you the operation can get quite complex. One can certainly appreciate that most of the time the operation just happens silently in the background. A whole book could be written about the TCP protocol. In fact, many excellent books have been written on the protocol. This section is a quick overview. If interested, the TCP/IP guide is an excellent free resource that you can use to dive deeper into the subject. Okay, so big props for this book for showing free resources. They really kind of, and not perhaps, just marketing another book they've got or something. That's something I really like. And this looks like it's from the creator of Nmap, I believe. So yeah, this is going to be a authoritative source on TCP. Really, really good link to a really, really good resource. So big props on this book for propping up those free resources and not just trying to make a buck on people who are perhaps a little bit internet illiterate and don't understand that you can find things that are freely available. You don't have to pay for for everything you want to learn about. All right, so I'm going to end it there. It's 12:01. I got to switch over to, I might eat something and switch over to my JNCIE series. So thanks for watching. I'm going to bookmark this so I can just jump right to it next time. And stay tuned for more.